This is Mrs. Palmer-Quay with the third video for Module 14. We are continuing our discussion of kinetics by looking at catalysts. A catalyst is any substance that increases the rate of a reaction without becoming part of that reaction or being changed by that reaction itself. Generally, a small amount of catalyst can change or can affect the reactant rate of a large amount of reactants because it's not being changed. So it just can be recycled. Once it has catalyzed one reaction with a little bit of reactants, it could go back around and do some more reactants and come back and do more and do more. Remember when we're thinking about catalysts that the word spontaneous when we're talking about reactions does not mean fast. It just means it's going to occur. Hydrogen peroxide, H2O2, will decompose into water and oxygen, and this is a spontaneous reaction, but it is a very slow spontaneous reaction, which is a good thing because otherwise we'd never be able to buy hydrogen peroxide in a bottle because it all will have decomposed into water and oxygen. However, if you add a catalyst, like some manganese oxide, then you could have a very impressive spontaneous reaction with water vapor just bubbling out of this Erlenmeyer flask as the hydrogen peroxide decomposes into water and oxygen. So this catalyst moves the reaction rate up from its very, very slow speed to a very, very rapid speed. But we could collect the manganese oxide. It's going to be sitting there in the bottom of the Erlenmeyer flask. In fact, we could just keep on pouring more hydrogen peroxide into this flask and watching it decompose because the reaction does not affect the catalyst. It is completely unchanged. A catalyst can work in several different ways. Remember collision theory, reactions don't happen unless collisions happen with enough energy and in a proper orientation for molecules to come together. And so a catalyst can increase effective collisions by actually holding reactants in the correct position. And it can help lower activation energy by weakening the bonds through the molecular attraction between the catalyst and the reactant. And so an example of this is ethylene gas and hydrogen with nickel as a catalyst. So we have a plate of nickel here, and it will attract the hydrogen and sort of break the bonds that the hydrogen has with each other and form an attraction with the nickel. It also attracts the ethylene gas, and then allows them to be closer together and have the hydrogen transfer its allegiance to the carbon, move away from nickel to bond with the carbon. And so this is one way that a catalyst can work to increase the collisions and lower the activation energy. Another way a catalyst can work is by providing another path to the end. If you remember, Hess's law tells us that it doesn't matter how you get to a final product, that the enthalpy of formation is going to be the same. And so if you have a catalyst that can take a different path to the products, and if it is a path that doesn't need as much energy to happen, then the reaction will happen faster because you don't have to have so much activation energy put in. So we've got a little diagram over here that's showing us that with the catalyst we have this reaction that takes two bumps to get there. So it's got two sort of intermediate compounds or reaction intermediates we call them, instead of the original reaction which needed this amount of activation energy to get going. The end product is the same. And the reaction can be diagrammed out by something like this little setup here that says for x plus y equaling z, you add the catalyst, and first the catalyst reacts with x, and then giving you this compound, a reaction intermediate that's xc, and then that reacts with y, giving you another reaction intermediate that is xyc, and then that reacts with z, and the catalyst sticks with the z, leaving x and y, or transfers x and y into z, and then the catalyst leaves, leaving z by itself. Many catalysts are specific to a reaction. Some metals are able to work with several different reactions, but not any one catalyst is going to always work. The book talks about heterogeneous catalysts, which are catalysts that are in a different phase of matter than the reactants. These are often also called surface catalysts and are metals, like that nickel that we saw back several slides ago. And in a surface catalyst, the reactants adsorb themselves to the surface. They don't adsorb with a B, but they adsorb. They stick on just a little bit because of some attraction, some electrons maybe are pulling the reactants in, and then they're held into position until the reaction happens. The catalytic converters that are in our cars are a great example of a heterogeneous catalyst. And so in these catalytic converters, you have these screens of metal, often platinum or palladium or rhodium. And the engine gases are sent through the catalytic converter, and the metal serves as a surface to collect molecules and encourage the changing of unbroken down hydrocarbons and carbon monoxide into water and carbon dioxide, which are not toxic and not a problem the way carbon monoxide is. So the catalytic converter in a car is a good example of the heterogeneous catalyst. A homogeneous catalyst has the catalyst in the same phase of matter as the reactants, and we see this often in reactions that occur in solution, like everything that's going on inside your body right now is a catalyzed reaction that's occurring in the solution in your cells, since you're about 60 to 70% water. So your biological enzymes, which are the words that we use for catalysts when we're talking about in living things, are homogeneous catalysts. And this little picture here shows how we envision now these enzymes, to call them by their biological name, how they work as the compound that is working on the reactant is called the substrate. It binds to the enzyme at a place called an active site, like the substances will adsorb onto surface catalysts. The enzyme will then cause the reaction to occur and release the products. Then the enzyme goes on to catalyze another reaction. Catalysts are extremely valuable. They are very, very important to industry. Some of the key products, ammonia is what's used for fertilizer. Most of our food sources coming from farms that are using fertilizer. Ammonia also can be transformed into things used in explosives. Petroleum products, along with the gasoline and fuel oil and the various things that come from petroleum, catalysts help us to manufacture those products, and many, many common chemicals are just made much faster and much less expensively because of catalysts. And then, as I mentioned, catalysts are essential for life. In this case, they are called enzymes, protein molecules, but what those protein molecules do are cause reactions to go faster, cause them actually to happen at room temperature when we need them to. And so enzymes, without enzymes, we would not be live. Remember with the energy diagrams that catalysts do not change the enthalpy of the reactants or the products. The energy values of where the reactants and the products end up on the energy diagrams stay the same, but they change the rate of the reaction. With a catalyst, a reaction will happen faster, sometimes extremely much faster, so that is where the change is. And in the energy diagrams, we only are able to show the energy used. We don't give a sense about how fast this reaction is happening, but we can say, look, with a catalyst, this is the maximum amount of energy we need instead of this much. So that finishes what I want to say about catalysts. This is the last video for this particular module.